Hey everybody, welcome back to another rant from Robison. And yeah, we'll keep going. So we've covered this idea of Taylor expansions, and coupled with the imaginary number, we've been able to come to Euler's relation. Euler's relation. Okay. And that gives us some connection between an imaginary number in the exponent's position and our cosine and sine functions, our periodic functions, if you will. Now, what I failed to mention in the past video is this part that does not contain the imaginary number is sometimes called the real part. And then this part is called the imaginary. Okay. And so sometimes you'll see you'll see this real portion, and you'll see this imaginary portion. You'll see these kind of notation there, just to indicate what section are you talking about. Well, we'll need that. That will come into play when we deal with the topic of today's conversation, namely second order differential equations with constant coefficients. Okay. So that's the topic of today's conversation. And technically, I guess this approach would could be used for not only second order, but higher order equations. So as long as they have constant coefficients, this should be applicable to even higher orders. It's just that it's most useful for these second orders, as you will see in a moment. So let's get at it. So the first thing that we should ask ourselves is, what is a second order differential equation? Okay. And we've seen examples of first orders. Second orders would be where you're taking two, for example, time derivatives. Okay. So acceleration, or Newton's second law, would be considered a second order differential equation, right? If you went F equals ma, and we wrote a in its differential form, you would have something like F is equal to m d squared x dt squared. So these techniques could be used far beyond just here in this class. You could use these in mechanics. You'll see it in E&M as well. So here's the general idea. Okay. You have a second order differential equation. So I'll just call it coefficients. I'll say a, and we'll use x as our variable here, plus b plus c. And we'll go ahead and use a homogeneous case for right now. So I'll just use 0. Now you could do this for the inhomogeneous case. I believe so long as this number, it's either a constant or it has a periodicity to it. So we'll have to double check that. But as long as it's a constant, this still works. Okay. So what's the general technique for this? Okay. And here we're going to use a technique, essentially guess and check. Guess and check. So we're going to guess a solution, and the solution to guess is e to the x. Okay. And I'll put an r in here as well. Sometimes you'll see this as an rx, or you'll see it as an s. Okay. This r represents some constant. Okay. And so the thought process goes like this. We are going to guess a solution in the form e to the rx. And after guessing that solution, we are going to construct what r has to be in terms of our constant coefficients in order for the guessed solution to work. So we're going to guess e to the rx and then find out what does r have to be in terms of a, b, and c in order for the solution to be correct. Okay? So let's go ahead and do that. If we have this differential equation, the second order differential equation with constant coefficients, and we guess that our solution is of this form. Excuse me. Let's get rid of this. I should say e to the rt. So we assume that x is of the form e to the rt. Let's go ahead and put that in. And one of the nice things is, of course, that when we take derivatives of e to the rt, those derivatives are fairly easy to calculate. So I'm just doing the derivatives right now. Excuse me, I dropped an x there. Yeah. Now, couple things to note. First of all, I've done the derivatives. Every time I have a derivative, I get another factor of r out in front. So 2 derivatives, I end up with an r squared. 1 derivative, I get the r. 0, there is no r out front. Okay. So you can see how if you had 3 derivatives, you'll have an r cubed term, or 4 derivatives, an r to the 4th, etc., etc. So that's one thing I want to mention. The second thing I'm going to want to mention is notice that for all values of t, e to the rt is never equal to 0. Okay. That's very important. And hopefully you see why, is that notice for each of these, I have this term e to the rt still. It's easy to take a derivative, and second of all, when I take a derivative, I end up with the same function again. Okay. That function can never be 0, and so it is perfectly permissible for me to divide both sides by e to the rt. Okay. Right, and that's where that can't be equal to 0 part is very important to emphasize. And so we say, oh goody goody, and we end up with this expression, ar squared plus br plus c equals 0. Now in math terms, if you run into this in a math class, this is what's called the characteristic equation. Characteristic equation. And you generally use the characteristic equation to determine what r has to be in terms of a, b, and c. So you say, well, I've got this. This is no problem. I have a quadratic equation. And so I know that the solution is simply the quadratic equation. 4ac square rooted over 2a. And we're done. Now I'll again re-emphasize, notice that if r is this value, either of them, right? There's 2 values here because of the plus or minus. If r is that value, then this guess solution is the answer to that differential equation. And we've solved it, right? We have now guessed the correct solution. Pretty cool. Okay. Now, hopefully you also see how this could be extended to higher order equations. But then you also understand why it's particularly useful for second order equations. This technique could be applied to a third order equation, It's just that finding the solution to the characteristic equation is not particularly straightforward. It's not particularly easy. Okay? Certainly not by hand. You have to go and plug it into MATLAB, for example. So this idea is perfectly generalized to higher orders. It's just not necessarily useful for those higher order equations. Life goes on. Okay? Good so far? Okay. So let us now come to a more practical matter, our RLC circuit. Okay. And in fact, let's go ahead. Let's set it up. We have a potential supply. We'll start off with a potential supply V. Okay. And let's go ahead and get an idea about, there we go. Just being really careful here. We'll do an RLC circuit where everything is in series. Okay. And what do we want to do? Let's go ahead and solve this circuit for the current running through the circuit. Okay? So I'll walk you through this at the very first. At least actually take a minute, see if you can come up with the differential equation. You got it? Yeah, good. And I should say, let's say that we had a switch. Excuse me. Let's go ahead and have a switch that closed at time equals 0. Okay. That'll just give us a changing current. If it's sitting there for a long time, then nothing happens. So let's assume that we have a changing current. Okay. So, well, KCL is not going to do us very much good, right? We only have one loop, so we're out of luck there. But when we apply KVL, okay, since our inductor, our capacitor, everything is uncharged, all three of these circuit elements are going to act like drops when the switch is closed. Okay. And so I can write my KVL equation. It will be lowercase v, is equal to, well, let's go ahead and go through. We have our lowercase I times R, the drop across the resistor. Then we have the drop across the inductor, di dt. And finally, the drop across our capacitor. Okay. Now, here's where I'm going to do a little bit of magic, right? First of all, let's go ahead and, well, we've got two things here. Excuse me, that's not time varying. This is a constant. Okay. At time is greater than 0, this is a constant. Let's go ahead and take a derivative. So we get 0 equals, and now what do we have? We have L d squared I over dt squared plus R di dt plus 1 over c di dt. Ta-da! Excuse me, you should yell at me. That's not di dt. I got carried away. This is just I. Ta-da! Right? Look at this. We have written down our RLC circuit. We wrote down the equation for the potential. Because this was a constant source, I went ahead and just, took a derivative, and we end up with this expression, which is exactly the equation that we were just talking about. It is a second order homogeneous differential equation with constant coefficients. So immediately, we can make our guess of the solution, the current as a function of time being and I'll put in some amplitude here for completeness, some amplitude e to the r times time. And what we are left to do is find out what is the value of r in terms of our constants, the inductance, the resistance, and the capacitance. Well, we've already kind of given away a little bit, but if we go through, so if we plug this in and simplify, we end up with a characteristic equation, L squared R, capital R, times lowercase r, plus 1 over c is equal to 0. And we're at a place where we apply our quadratic formula. So at the end of the day, what we have is little r equals negative resistance plus or minus resistance squared minus 4L over C, that's to the 1/2, over 2L. And in fact, I'm going to take that 2L, so we get this, negative R over 2L plus or minus, and I'm going to go ahead and move the L into the square root. So I have R over L squared minus 4 over LC. Cool, right? And then we're done. Well, there's more to be continued. Now you notice the reason I kind of did that, you have this R over L, and from your studies of RL circuits, you know that that would have been the time constant for the RL circuit. Okay. And also you notice this LC, so we think of RL as being a time constant for the RL circuit. This 1 over LC is related to the natural frequency of the circuit. So when we were dealing with LC circuits, you had that oscillatory nature that was dictated by 1 over LC. Okay. So you can kind of see already that little r has a mix between that exponential decay and the oscillatory nature. Okay? We're going to focus in more on that. So we have our final solution already. We have that our current as a function of time is going to be some amplitude, E, okay, to, I'll call it the R plus T, and then I'll go ahead, because both of these serve as a solution, I'll call it B, E to the R minus T. Okay. Where I am defining R plus or minus as being, we have that 2L, whether we have the plus or minus sign right before that square root. So both of these count as answers. Right? Both of those are appropriate answers for this thing. So technically, the current could be a linear combination of those two answers. Now we'll have to have a discussion about how to get the values for A and B, and those will come from our initial conditions. Things like having the current at 0, right, the moment the switch is closed. For example, setting that current equal to 0. Okay. Or having, the potential drop at 0 being equal to V, okay, across the inductor, for example. Okay, so we'll not worry about that right now. We'll see when we're going through and solving additional problems, or maybe at the end we'll go back and get those A and Bs. Okay. What I would like to think about for a moment here is the behavior of the current based on the R plus or minus values. That's the thing that I think it's probably more important to stick with for right now. Okay. And you'll notice we actually have 3 scenarios. Okay. One scenario is when R over L is greater, well, okay, I'll put R over L squared is greater than 4 over LC. Okay. So that's situation 1. And you notice in that situation that both R plus and minus end up being real, right? If R over L squared is greater than 4 over LC, then this term in the square root is greater than 0. Okay, right? This term in the square root is greater than 0, and so R plus or minus end up being real. And in fact, furthermore, both R plus and minus end up being less than 0. In other words, my current will have 2 exponentially decaying terms to it. So I'll put a magnitude sign in here for a second, just to highlight the fact that both of those terms will have a negative sign. They'll be exponentially decaying. Okay. Nothing too exciting there, I guess. You've kind of already seen some of these kind of double exponentials. Okay. So let's go to a different scenario, and this is the one that will latch on to the previous discussions. Okay. What happens when R over L squared is less than 4 over LC? Right? That's the curious case. Well, let's look at that for a second. R plus will be equal to negative R over 2L. And we'll just take the plus for a second. And then what do we have? Well, if R over L squared is less than 4 over LC, this means that R over L squared minus 4 over LC is less than 0. So I'm going to swap the order here. So what I'll have here is I'll put a negative 1 times 4 over LC minus R over L squared. And that whole thing is square rooted. Now keep in mind, this term now, because I've swapped the order, this term is greater than 0. And notice I have that negative 1 explicitly written. Well, what does this mean? Well, okay, if I'm dealing, let's just put the minus in. Okay, well, what does that mean? I have R plus or minus equals negative R over 2L plus or minus, and now I'm going to take that negative 1 and pull it out. I'm going to apply the square root to negative 1. And so what do I end up with? This j, the imaginary number, over 2 times the quantity 4 over LC minus R over L squared, square rooted. So if I'm thinking about my current now, and this is why I had to discuss Euler's relation, if I go back and think about the current now, I of t, it's interesting. Let me e to the r plus t. Let's just consider this first expression, and we can see the second one as well in a moment. What does this mean? This means I have a e to the negative r over 2l. And then I have e to the j over 2 times 4lc minus r over l squared to the 1/2. Okay. So what do I have at the end of the day? I have a combination of two effects. The first one is an exponential decay with that time constant, r over l. Okay. The second, so that's the exponential decay. The second factor, because of Euler's relation, the second factor represents some sort of oscillatory term, right? This is a fancy way of writing sines and cosines. So this e to the j over 2, blah, 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 represents some sort of oscillatory term. And so what can you think of when you take those two together? I have an exponentially decaying amplitude multiplied by some oscillatory term that stays constant in terms of amplitude. And so when I take those two and put it together, what you should end up with is some sort of oscillatory term, or some sort of oscillatory thing that has an exponentially decaying amplitude. So if you could actually plot the amplitude here, that dashed line would be negative e to the negative r over 2l. And then this sinusoidal or cosine term would have this frequency, this 4LC minus R. So the frequency of this, how quickly, it repeats. It's cool, huh? Okay. And of course, let's get rid of this for a second. Of course, if I included the second term in here, you would have something like plus b e to the same, this r over 2l, and then e, and then instead of a positive, you'd have that negative over LC minus r over l squared to the 1/2. So this situation where you end up with this oscillatory behavior because of the imaginary number coming into the expression, this is sometimes referred to as an underdamped circuit. Now, for completeness, you say, well, Greg, what happens when I have r over l equal to 4 over LC? What happens in this situation? You notice that r plus or minus ends up becoming, we'll say r over 2l plus or minus 0. The square root is 0. Okay. It turns out that, so r plus or minus end up being the same value. Okay. Now, I won't actually go through the derivation in a video. So I'll leave that to you for your reading if you somehow, say you have trouble falling asleep at night or something like that. Okay. You never know. It happens. Okay. So this is called a situation with repeated roots. repeated roots. Okay. And that's because the r plus or minus gives you the same equation, or the same exponential. Okay. What the actual solution is here, if you're dealing with a second order differential equation, the solution is actually going to be something along the lines of the exponential decay, this e to the negative r over 2l times t. Okay. And rather than being times a plus b, so those two coefficients, if you will, okay, you end up with this. You end up with a time in here. Now you can go back and double check that. Okay. What this solution is called the critically damped solution. Okay. And what this is that for small times, when t is really small, this linear behavior is the dominant term. Okay, so if t is small, this is close to 1, and so this t is the dominant term in the response of the circuit. But at large times, as time increases, this exponential term ends up being the dominant term. So for short times, you'll see a linear relationship, and then at long times, it'll be an exponential decay. One of the other cool things about the critically damped is that it gets to 0 the fastest. Okay, I won't prove that, but I'll say goes to 0. I'll put fastest. So you could see for the underdamped situation, it goes through 0, but it doesn't settle down. It oscillates, and that oscillation will take a bit of time. For the overdamped situation, it actually, again, doesn't go to 0 as fast. Okay. Critically damped is like that perfect, goes to 0 without, any excess time. I'm just talking. Okay. So you have your three situations. Okay. Well, we should probably go ahead and solve our RLC circuit now. We have our situation. Okay. We have our final answer. Our R plus or minus has to be equal to R over L, 2L. I'll write this down again. R over L squared minus 4 over LC to the 1/2. Okay. And notice your choices of the parameters R, L, and C will determine whether you're overdamped, critically damped, or underdamped. Okay. The other thing that I would like to think about is how to get those coefficients A and B. So we had I of t is equal to, let's go ahead and assume that we're underdamped. Now let's say overdamped. Let's go ahead and assume that we're overdamped at the moment. And so we'll assume that the equation has the form e to the r plus t plus b e to the negative r minus t. I always get that mixed up. Okay, so let's assume that we have an overdamped situation. Here is our final expression, and we would like to know the values of A and B. What are these going to be equal to? So one of the initial conditions, we can say something about what the current should be at time equals 0. Namely 0, right? The moment that the switch is closed, because the inductor is uncharged, the current flowing through the circuit should be 0. So now that I have my general solution for the situation, I now need to tailor it to my given values. Right? So let's go ahead. Let's go ahead and say that current at 0, and what I can do is plug in 0 for the time. So I have e to the 0 plus b e to the 0. Of course, e to the 0 is 1. And so I end up with my coefficient b must be equal to negative a. Oh, that helps out so much. Right now, I can write I of t is equal to a, and I'll put in here e to the r plus t minus e to the r minus t. And I can go even further. Notice that both r plus and minus have that common term in there, that negative r over 2l. Okay, so let's go ahead and plug that in. So I have a e to the negative r over 2l, and then I'll have something like e to the, let's just call this c for right now. C's bad. Let's call this fancy c. Okay. That's probably not a good idea either. Let's call it theta. Let's just call it theta for right now. Okay. So I have e to the theta t. Oh, that's bad. Let's call it omega. Good gravy. There, we'll call it omega. So I have e to the omega t minus e to the negative omega t. So there is one situation. Excuse me, I dropped a time here. There should be a t here. Good. Yeah, okay. Well, let's go ahead and see if we can find another expression. We need another boundary condition to give us what the value of a is. Well, let's see. I was thinking usually boundary conditions, good places to look are at time equals 0 and sometimes at time equals infinity. Okay. And again, at time equals infinity, our capacitor should be fully charged. And so the current should drop to 0 again. But we see that doesn't really help us because this common term already goes to 0. So that's not going to help us too much. What can we say? Yes. Okay, I think the other one's going to be in the derivative. What can we say about di dt at time equals 0? And thinking about the inductor for a minute. Yeah, good. So the inductor, the potential drop across the inductor at time equals 0 has got to be the same as the source, right? Has better be the same as the source. No currents flowing, so the capacitor's uncharged, the resistor's doesn't have any current going through it, and so the full drop had better be across the inductor. So I'm thinking that di dt better be equal to v over L. And that should help us find this value of A. You ready for it? Let's get at it. Okay, so we better take a time derivative of the current. So let's start off there, dt. And so what do we have? We have our constant A times negative R over L, 2L, e to the negative R over 2L time. And then we have this e to the omega t minus e to the minus omega t. Ugly. I'm product ruling it. And then we have plus a e to the negative r over 2l t times omega e to the omega t plus omega e to the minus omega t. Oh, that's ugly. But now that we have that expression, let's plug in time is equal to 0. And I have the potential drop across the potential of the source divided by the inductance had better be equal to A times negative R over 2L. And I have e to the 0, so I get 1 times e to the 0 minus e to the 0. Uh-oh. Life got easy real fast, didn't it? Then I have the second term, a e to the 0 omega e to the 0 plus omega e to the 0. So right here we see, that's 0. This is 1, that's 1, and that's 1. And so what do I get? I get V over L equals 2 omega times A. And now you can see why I used omega, right? So you have V over 2L omega equals A. And just to remind you, what did omega equal? That was that R over L squared minus 4 over LC to the 1/2. Okay. Cool. So not only does the solution, that R, depend on the resistance, the inductance, and the capacitance, but our amplitude A is also dictated by the resistance, the inductance, and the capacitance. So what do we have at the end of the day? We have that our current as a function of time equals, we have a value for A, the potential over 2L omega e to the negative R over L times time. And then I'll put in here e to the omega t minus e to the minus omega t. Okay. Where omega is equal to R over L squared minus 4 over LC to the 1/2. Double check me. I feel like I might have dropped a 1/2 out in front. So go back, check your notes right now, but I think there's a 1/2 there. Okay, I'm going to go back and check myself. Okay, cool. For those of you that are really, really interested, you might recognize this as being, let me think here. You might recognize this as being a hyperbolic function. And in particular, I believe this is sinh. So for those of you that are burning with curiosity, I believe e to the x minus e to the negative x divided by 2 is defined as the sinh function, the hyperbolic sine function. Notice I don't have imaginary numbers in the exponents. Okay. And for completeness, if you're interested, this is defined as the cosh function, the hyperbolic cosine. Again, you don't really need to know that. It's just that sometimes it's just nicer to write it out, but it's nothing that you have to know. It makes the solution look simpler, but otherwise, yeah. Okay. And we're done, right? We have now solved the RLC circuit that is overdamped. Here's our solution. You don't know? Maybe? Okay. So I think that's a plenty for right now. What I'll do, let's see. Go ahead and think about how the approach changes if you did a underdamped solution, or if you did a critically damped solution. Think about how does the process change to find the coefficients based on the initial conditions. Okay? That's the first thing. Second thing, take it as good practice. Go through and see if you can come up with those coefficients. Okay? And that's the second one. And yeah, I'll leave it at that for right now. So the next video, we'll go ahead and look at, say, a couple more RLC circuits. Maybe we'll put them in parallel. Maybe we'll do some kind of funky combination just as another practice step. Okay? Hey, thanks for your attention. I'll see you next time.